Good evening, everybody. Mars 500 is a remarkable set of analog experiments that involve multiple nations, and it's been beautifully orchestrated by our colleagues at the Institute for Biomedical Problems in Moscow. The current 520-day study that's underway, now day 351, so the crew's on their way home. And it's been an incredible amount of planning and the details involved with implementation, not only for the facility, but for the more than 100 scientific experiments that are involved in this unprecedented study. And it's my pleasure to introduce my friends and colleagues, Dr. Igor Yushakov and Dr. David Dinges, who are going to update us on the Mars 500 and some of the research studies that are taking place in this important international study. So Dr. Yushakov is going to start, and then we'll be followed by Dr. Dinges, and then there'll be an opportunity for questions and discussion. Thank you.
Добрый вечер, дорогие друзья.
Good evening, dear friends.
Мы сегодня имели счастливую возможность
Today,
собраться вместе
we were
и
fortunate enough to get together and to talk.
слышно?
Can you hear me? Is there an interpreting?
Поговорить о прошлом космонавтики,
To talk about the past of the cosmonautics, about the present, and to dream a little bit about the future. There was a very emotional conclusion of today presented by Charles Bolden, and somehow I felt my mood has lifted, and some of my colleagues also felt the same. I would like to tell you in brief about our experiment, although it has been done more than once, but now it's in its stage of completion or its final phase, and perhaps you'll be curious to find out how it was going, how it's ongoing, and how it's going to be completed. The thing is that for today, it's 351st day of the experiment, and 170 days, or to be more precise, 169 days left to the completion of this experiment, and it's going to end on November 5th of 2011. Which is the anniversary year for manned flight. The experiment started, I'll remind you, on June 3rd of last year. So the duration of the experiment is 520 days. Let's start with this picture. And of course, let's get started with Yuri Gagarin and his 108-long-minute flight, which has been mentioned many times today, and from which we have been counting all those wonderful decades which we have discussed and which we have delineated as our future plans. The duration of flights has been growing steadily, both for the Soviet and American programs. The record duration of flight is 438 days, Valery Polyakov, Mir Station. And the minimum duration of Mars mission is a little over 520 days, and this is what is being simulated under conditions of this experiment. Record breakers of space medicine and space physiology, and we have heard a beautiful presentation by Vladimir Titov. He is one of those legendary four figures who have accumulated a year and more in one flight. And today it's been mentioned correctly that many cosmonauts who have been in a long-duration flight, we talk to them and we keep asking them these questions, and and today it's been mentioned, Dr. Inessa Kozlovskaya mentioned that of course this is not the limit, and it's very likely that the flight duration
or
duration of being in microgravity conditions or zero gravity condition during a year and a half is quite possible. But the Mars expedition has some other factors which have to be taken into account. It's been spoken much today, mentioned today about the analog experiments, and this is indeed a good path which allows to study the mechanism of the affecting factors more completely, and on the other hand it saves a lot of money because they are used. The very fact that those studies are used for researching various factors in model conditions, hypokinesis, for instance, short radius centrifuge, and such project as Mars. Of course, given the conditions of the experiment, we won't be able to simulate all the factors, but we would be able to simulate those factors which are demonstrated on this slide. Their overall characteristic of the expedition itself. Those are the factors of the enclosed environment of habitation, and psychophysiological factors, which are one of the two major barriers or obstacles for flight in deep space, along with radiation. Those factors which are too complex to simulate, they're also provided on this slide. There is a large number of those factors as well. And we have the data for orbital flights, radiological flights, experiments, and higher hierarchy animals. Based on those experiments, we can build a so-called mosaic as a forecast of risk factors, taking into account the knowledge that we accumulate that affect a living organism. So these factors should be collected based on separate experiments, and they should be put together as an overall global picture of forecast. As far as the Mars 500 experiment is concerned, Mars 105 experiment preceded Mars 500. Many of those people who are present here are our partners, perhaps, or were either opposed to it or they are aware of that experiment. It's an international experiment, and it was conducted under the aegis of Roscosmos, Russian Academy of Sciences, and of course the Space Agency. 4 Russian members participated and 2 European participants in that experiment. That particular experiment had a goal of working out the techniques, the methods, or the entire range of issues or problems, starting with selection to rehabilitation after the experiment. The experiment was successful, and it had demonstrated that international cooperation is ready to conduct Mars 500 experiment, which has been started on June 3rd of 2010. There are also 6 participants in this experiment. 3 of them are Russian participants, Russian citizens. 2 are European Space Agency representatives from France, Italy, and respectively, and 1 additional participant that we attracted, a representative of the Chinese Republic. And I must say that we're very happy with this crew composition, because in addition to the fact that the experiment has become such a Eurasian experiment, it has also contributed a very good crew member to the team, and he has become a link among many of the other crew members. the goals are similar or almost the same to study the factors of life in enclosed environment, isolation, and all the accompanying psychophysiological factors. The ground experimental complex where the experiment is being conducted, probably this is not a new slide for you, but the overall scope, the overall size of the complex is over 1,000 cubic meters, and it contains all the necessary supplies of food, water, repair necessities, maintenance, medical complex, exercise complex, and also devices and rooms, for instance, hothouse and other rooms that are necessary for a human being to exist in such conditions. The goals of this project are absolutely obvious. And in general, generically speaking, they allow to obtain initial data on the one hand on the evaluation of the effect of the factors on the human body, and on the other hand, they may serve as initial data in order to build interplanetary complexes. And of course, although of course this is a more complex task, and it has not been posed as the main task of this experiment, but as a derivative, it was understood. Various situations were studied, various conditions for activity of the crew. They're shown on these two slides. I'm not going to list them all. I'm going to mention only that each of the crew members, in reality, and it has been demonstrated by the experiment, each crew member had to perform a task on 5 or 6 disciplines. There are 2 physicians as a part of the crew, and naturally, all of them had to perform some technical tasks, and a 6-member crew, if you were to compare it with the submarine, then a submarine crew also has to perform multiple functions, and here those are multi-functional functions. At the present moment, the crew is at this stage, 351st day, and what is left is a heliocentric orbit flight, and also within the gravity field of the Earth, with completion of the experiment on November 5th of this year. These are the same flight stages, only here they are presented not in days, but in flight stages, the appropriate stages. Based on the selection, and selection was very lengthy, was preliminary for a long time, and naturally, initially, there were requests which were collected from all over the world, and afterwards, the selection took place on the basis of our institute. And total, altogether, there was it took about 2 years. It's a significant period of life where the participants in this experiment accepted those constraints in order to participate in this very complex experiment. Also, a few words about the crew. I've already mentioned certain things, but the structure of the crew includes 2 doctors, 1 flight doctor, flight surgeon, and 1 doctor that is a specialized physician, and 2 researchers and 2 crew members who also conduct research, engineers, scientists and engineers, and of course the commander. And the commander heads the international crew. This is the crew, including the backup crew, at the final selection stage. It's virtually a double crew, and the main crew is and the backup crew, and this is a few weeks prior to the beginning of the experiment. What was very difficult was psychological selection, including many various stages. There were complex tests that were administered, and it was which detected psychophysiological resistance of the organism in extreme conditions, in survival conditions, in hardly inaccessible locale, and of course there were no cold Martian conditions simulated, but nevertheless those conditions allowed to reveal a more tight combination of its participants, and they allowed to evaluate the crew activity in such rather complex conditions where they might turn up, if not on Mars, then upon return from virtual flight. One of the moments that is related to the simulation of trauma, a fracture. So this was done in difficult winter conditions. The types of activity are varied. I have mentioned that in the past. What is really helpful is our partnership with our American colleagues, and it will be mentioned in the presentation of my colleague David Dinges, and therefore I'm not going to dwell on it in great detail. It's very important that the project is international. There is a total of 105 scientific projects. 1/3 of them are international, including ESA and other countries. Among the American participants, those are, of course, right, and those experiments that will be discussed in the presentation. So there are Europe, America, and Asia. All of the experiments may be subdivided into clinical, physiological, psychophysiological, sanitary, hygienic, and also operational experiments. Most often, those are a combination of a few various areas. There are not solely psychological experiments, there are also biochemical. They have biochemical components, so these are all integrated, but this subdivision is provisional. Some features of certain experiments are shown here. Selection of food items. Of course, food is one of the most complex problems, and our German partners were of great help. They also used to help us during the Mars 105 experiment. And this problem remains the same also in this experiment, that it's that the help, the assistance that we received from our German partners afforded us to create balanced rations, and also to obtain unique data on metabolism in conditions of pure, so to speak, as a pure experiment, medically speaking, and to get the data which have been in part published already in some of the major journals, such as Nature, on lithiolite excretion, and on measuring certain parameters And this is the kind of data that is from the point of view of maybe they're not indicators, but as far as the purity, the accuracy of the experiment conducted in the same conditions, they are extremely unique experimental data. What was also important was that prior to virtual landing on Mars, there was a simulation that took place of hemodynamic effects. It was done on day 251 and 257, when the participants attempted to simulate or to make the activities that they performed in their spacesuits more complex during the EVAs, in such a way so that immediately a week prior to the EVA to simulate some unfavorable effects that were related to the motion of fluid media in the organism. And they used the anti-acceleration spacesuits in order to simulate motion of bloodstream to the upper body, and at least in part to simulate the situation which may arise during transition from a state of zero gravity to state of 0.38 g in conditions of the surface of Mars. Well, here you see that they are measuring parameters in conditions which were conducted in the chamber, directly in the chamber. The effect of Mars, the surface of Mars, 3 crew members, and that is a separate team, part of which was a European member, a Russian member, and a Chinese member. And approximately a week prior to virtual landing, they have selected that team in the smallest module with a volume of 50 cubic meters, and they performed a simulation of Mars landing with the subsequent activities, and they performed the 3 egresses in new experimental spacesuits, which were provided by the scientific enterprise Zvezda. This is a well-known company in Russia which provides spacesuits in our country. And a spacesuit weighs 32 kilograms. Of course, this is an experimental sample. And you can imagine that 32 kilograms is, if a spacesuit were to weigh 80 kilograms, or considering a gravity of 0.38 g, we arrive at the weight which realistically is very difficult to work in.
Spacewalks were of the same typology. And they contained operations that had to do with promotional activities, PAO, and such. Science program, soil sampling. I'll try to give you a better picture of that in the short video that's coming up. And a number of other activities as well, all intended to be conducted based on preliminary arrangements with the key participants, such as RSC Energia Corporation, etc., that provided the near-flight hardware in order to replicate and imitate the real environment. Of course, some of the things were off the table, and of course, we had to model them using virtual reality assets. Both the first and the second and the third spacewalks were identical, except the spacewalkers were different. And all three of them would be landing on the Mars. 14th, 22nd, and 28th of February were the dates when these EVAs took place. It was covered fairly widely in the media, and there was a lot of publications to that effect.
Video, please.
Right now we're going to get a chance to enjoy this fairly short video that depicts one of the EVAs. And this would be the first of the 3 spacewalks. Suit donning. You can see the Chinese crew member helping the Russian crew member get into his suit. Flag installation. Russian flag, the ESA flag on the left. A Chinese flag on the right. Alexander Smolyevsky, a trained medical specialist, just said that this spacewalk is dedicated to the 50th anniversary of Yuri Gagarin's flight. Some pretty basic yet critical experiments conducted, as they were planned to be conducted. Soil sampling. The equipment used are the real flight hardware that were once manufactured in support of the Moon program. And the Mars program that was being deployed quite a long time ago, as we reminisced earlier today. Obviously modified and remanufactured. Those pieces of hardware that were designed a certain amount of time. Basically, you know, what we could have possibly manufactured if we were to quote go to Mars tomorrow. We had a movie once that was called exactly that. Tomorrow we go to Mars. So if we were to set our path and our goal to go to Mars tomorrow, quote unquote, these are the tools and the hardware that we would be bringing along. I've already said this, but I'll reiterate that adding a Chinese crew member to the crew complement was a successful, good move. He was doing a splendid job during those spacewalks and performed very well and was in good communications with the rest of the crew members who were on virtual orbit, quote unquote, as well as with both of the crew members who were out on EVA with him. During his 3rd spacewalk, he would don the suit all by himself. It was a full-on member of the spacewalk crew, and so both the Russian and the Italian and the Chinese crew members were all out there on the Martian surface imitator.
Something
that this video is not showing, but during the 3rd spacewalk, something that we did during the 3rd spacewalk is we modeled a crew being dropped on the surface, which is quite a hazardous ordeal. But the operation went over without a hitch. All the countermeasures and the safety measures were implemented to the T. A Mars rover model. This is the rover that was used in that experiment. This is not a high-fidelity mock-up. This is just a mock-up. But this was the rover that had the full capability of a Mars rover. It was its motions were modeled during the flight, and using this rover, they'll be able to assess all the functions of all the crew members, the motor function, that is. And these are the criteria that were used to select the 3 spacewalk crew members. Medical support, including daily medical monitoring activities and monthly sessions, more precisely every 35 days. And then each 6 months, an in-depth medical examination using very well-known techniques. All the parameters were processed, telemedicine-wise, and all the cutting-edge telemedical technologies were used. It's already been said today, but I'll reiterate it. Psychological support means were made available and were used. Basically, same set of assets that we currently have on board the ISS. But then we're also trying to hone in on some new technologies that we would be looking forward to implementing on station. But as a, using this test bed, it would be much easier to test run those technologies, and all the newest advancements that were made available to us, we tried to incorporate into this experiment. That's the crew. Some of the snapshots of some of the experiments. This is the kickoff of the experiment. This is Jeff Sutton. At the experiment kickoff ceremony, June 3rd, 2010, right before the crew ingressed the interplanetary orbital station. Thank you for your time. This has been a wonderful, wonderful day. Much success to everybody, and sleep tight. I hope every one of you is dreaming of Mars tonight.
So if we can get this switched over to my computer, we'll begin. I'm David Dinges from the University of Pennsylvania School of Medicine, and thanks to the NSBRI, I was able to represent the American involvement in the Mars 500 project, in particular the Mars 105 and 520-day project. Our focus was going to be on the behavioral aspects of the mission of the crew, and in particular something I call neurobehavioral, and I think it's important to just explain my use of words. So you'll almost never hear me say psychological. You'll rarely hear me say cognitive. I use neurobehavioral throughout the world because no matter what the audience is, everyone understands that the brain is the organ of behavior, so that's the neuro, and the behavior is the output of the brain, and that's the behavior. If I say psychological, some of you think I'm talking about motivated behavior. That's a tiny part of behavior. There's reflex behavior, there's conditioned behavior, there's differential vulnerability in behavioral responses, etc. I'm talking about all of it. So the focus is on neurobehavioral function. This is the facility that you've already seen pictures of, and what I'll do is just show you a little bit of the inside, then show you what we were doing and why we were doing it. And these were the opening ceremonies, and this is a little unusual. I'm a laboratory experiment that studies humans in a controlled laboratory environment for weeks at a time, hundreds and hundreds of people, thousands of days of study, always healthy people, half men, half women, average age 30, age range 22 to 50, 55. And we do a lot of work for different federal agencies on what is the capacity of a healthy, trained, motivated human to function under extreme conditions. In particular, how many days can you go without sleeping with high cognitive workload and maintain your a minimal error rate, etc. So and then what are the countermeasures for that? So my interest here was through the NSBRI to understand what would happen in this prolonged period of confinement. Why this experiment? Why not other analogs? Well, we do use other analogs, but what IBMP has done here is create a rare opportunity to put people who, they may not be astronauts or cosmonauts, but they're in the category of people who would become astronauts or cosmonauts, so they're surrogates of that at least. They're in a confined environment about the capacity of a spaceship. They're simulating a space mission, and it's 520 days, which is unheard of. If you follow the history of people confining themselves for studies, you know that in many cases, everything falls apart very quickly. And in fact, usually people who volunteer for those studies are the last people in the world you want in them, without being screened, right? You screen them, you might, then you have a better chance of being able to do it. I'm going to do the reverse of what I normally do. I usually wait to the end to talk about the team. But a key message here is not only that IBMP built this chamber and selected these people to run a Mars simulation mission and did it with a high degree of fidelity, but they also created an environment that would require teamwork on the part of the investigators. In fact, we built our own team from my laboratory, but because of the way we gather data, which I'll describe to you, and we're using the same techniques on space station, our goal as scientists are when we get access to NEMO or the space station or IBMP, it's to not only get the 10,000 data points we want, we don't want to lose a single data point, not one. What I never want to hear is we just lost a run or we just lost a bunch of data. And we want as much objective data as we can get, and we want to see it right away as we're getting it, and we want to check quality control, fidelity, compliance, etc. So that's the standard we hold ourselves to. Now the question was, could we do it working not in the US but in another country, with a facility that we weren't involved in building, that's powered its own way, etc. And how would we do it? And that took a team, and not just investigators from my laboratory, but a software company that programs a lot of our software, and a liaison person, our systems analyst, who we could send over. And the most important person that made it work was really Dr. Igor Savalev, who's here. He is a liaison person between us and the crew in the facility. And without that person, I don't know how we would have done this, actually. And you'll see. And then we had, of course, other collaborators involved. This is the facility without people in it, including mission control. And Dr. Yushikov didn't say it. I didn't hear him say it, but there were a lot of mission controllers. The numbers are, what, 20 or 30 or something, but a large number. So they're working 24 hours on shifts just like a real mission control would work. And then there's an exercise facility, command console, kitchen area. This is a living area. Behind it here would be the bedrooms. Of course, there are connectors to the modules, a bed area where one of the computer sits. Here's a medical module, working area. There's plants on board and research going on by other investigators, and there are ESA and many other Russian and other investigators involved in other studies. One of the challenges that we all face is as we pull data out, if we get all the data that we hope to get, if the crew's able to give us data on our systems and we can get it out and it's of high quality, now I've got to figure out why suddenly on one day the data look like something happened and the person's having a physiological or behavioral reaction. I have the same problem on space station, no different. And NEMO, same problem. The question is what happened operationally or what happened that wasn't operationally planned that I don't know about. And so part of doing these using quasi-experimental environments where I control the dependent variable but not the independent variable, except it's the mission protocol, is to, after the experiment, or during it when possible, line up all the provocative events with the data to also help with interpretation of the data. Because what sets these analogs apart, including space station, from a laboratory experiment is, in my lab, I control everything, but not in these environments. And of course, that's a disadvantage, but the huge advantage of these environments is they give me something that's more realistic to what the real world will be for the people experiencing the events. And this is the touchdown, and then there are 3 of the crew up above. This is the crew you've seen pictures of. This is the 105-day study. Now, a key thing that I think was visionary on the part of IPMP was to do a pilot study. This is painful. Funding agencies don't like this. What do you mean you need money to run a 105-day preliminary study? And they think, you know, it's a waste of time. And you run it and find out that many of the procedures you took to Russia and deployed don't work. And things break, or the crew won't wear the device because the fungus grows under it, or any number of things. Or they turn the lights on in a position that prevents you from recording the face, and you've got a face reading algorithm. I mean, you name it, and it goes wrong. Now, in our lab, we would normally run a pilot study, but we had to run a long enough one in the chamber, and the Russians had set up a 105-day, 2 Europeans, 4 Russian volunteers. And whenever I say what actually happened with that data, people say, oh, what a waste, what a shame. And I say, no, you missed the whole point. Because of that, we now have more than 95% data complete in the 520. It was the lessons learned from the pilot study that let us get the good data from the real study. And the lessons learned were the data must be evaluated regularly. We cannot wait to the end of the experiment to find out a device failed. We can't even wait 1 month. We don't want to lose anything. We need to look at it weekly if possible. We need to have backup equipment in the facility. Multiple computers, multiple wrist ActiWatches, etc. The computer programming has to be able to detect anomalies. What are anomalies to a behavioral scientist? Well, they're equipment failure. What else? Deception. Lack of adherence. Now, not for moral decisions, but for behavioral decisions. For understanding if someone will deceive you on a device that's measuring them, it's a bad behavioral sign for a mission selection. So we want to know the base rate of that in these environments. And so we have to set traps up like that make sure we can understand the data is the data and it wasn't made up or manipulated. The liaison facilitator I already talked about is critical. We realized we had overburdened the crews, like all scientists and all reviewers of science, because we got this with the ISS study we're doing. Reviewers said, measure them every day, twice a day. We ended up measuring on ISS every 4 days, and that's excessive, given the time and what the crew can tolerate. But scientists always, of course, want the perfect measurement regime. What was important about this experiment was 520 days. It was better to get fewer measurements spaced out, but get them all the way to the end. In fact, I always say that going halfway on this experiment is almost useless. Every day we go now, past today, is extremely valuable because we're getting in territory that we haven't studied before. Fewer tests, briefer tests, provide feedback to the crew. Some sort of feedback on how they're doing. It doesn't have to be on every test, but on enough that they understand that what they did worked. We got the data, they understand it, and they got some information. And I think these are generic lessons for analogs. In our experience, we get high quality and a lot of data from analogs because we do these things. Use only an optimal device for shared data. You can't put 5 ActiWatches on them. In a week, they won't wear any of them, in which case you don't get any data. Acquire the data with the best single device and then agree to share the data with others if you have to, if that's the requirement. And then the sharing, it's a complicated thing to share data. Complicated for scientists, complicated from a human ethics, identification protection, complicated for the funding agencies, but not insurmountable. It's just harder, and you just have to work it out. And we're in dialogue now with how to work it out and the data will get shared. We just want to make certain that various protections are in place. The video data, the face we were getting, we needed special lighting. We realized we had to redo our computer systems to do that, and then the scales in that had to be brief and translation. translation's everything, and we learned that even our best translators in the United States were Russian. When we got down to some of these scales, we needed Russians in Russia to do the correct translation, because some of the words we thought meant something in English didn't necessarily mean that in Russian. There's always a need to ensure the translation's correct. So you've seen these pictures of the crew selected for the 520-day. We learned our lessons and got everything ready, and notice this all occurred after ISMS last year, just after it. Here are the crew listed over here by their nationality and age and areas. And now I can't actually show you a lot of the data. As all of you know, there's a rule of science that says, and it's the first rule, you cannot allow the way you measure something to change the thing you're measuring. And in this environment, if we release information on a crew that's already identified themselves as being in the experiment, that's very unusual, right? Most experiments, people don't say, I'm in that experiment, which they have a right to, but they don't. They maintain the confidentiality. But this crew's being videoed, the media is watching them, etc. If someone releases data and they can tell, well, that's the third person or fourth person in the crew's data, we have now potentially identified someone, which is illegal and unethical in this country. The bigger problem is, even if they're not identified, but the information gets back to them, that there's a certain pattern developing, then it could change their behavior. They could alter it. And the whole point of the experiment is not to change their behavior. They should emit the natural behavior they would emit in this 520-day study. You have to view it, this is hard for a lot of people. A behavioral scientist does not manipulate the subject except in certain ways, and then watches the behavior of the organism. Okay? We don't want to tell them how to behave, we want to see how they behave. So this is, as we've heard, the experiment's about 3/4 of the way done. We have 95% complete data. Now, what does that mean? Well, let me just show you. These are our computers we put in there. They're special computers. We know the timing error in all computers. They all have them. NASA was shocked when we revealed what the timing error is on all their SSC computers, what assembly line they came off of, what day they were made, what the delay is in the key presses. And we make our assays shorter and more accurate by actually figuring all that out and then adjusting with software for the error in the computer to make the assay very sensitive. And so that's actually how we measure behavior with a great deal of precision. We had to light the face. We had to do all this in a fire drill because the bureaucracy of paper passing and getting agreements took months. Then they turned to the scientists and said, now you have 30 days to build all the technology to figure this thing out and make it happen. And it was a fire drill. This special light on the face, which is Velcro to the computer, has to light it so we can do video of the face to read per close and read, it's optical computer recognition to read emotion in the face and that, which I'm not going to show you. But these pads come from a special company that makes the backlight for computer screens. And then here's the ActiWatch over here. And then there's a special 19-volt transformer built into the computer. And then this was the hardest part. We had a little SD port on the computers. This is how we were going to get data out, and bought these SD chips and put them into the computer, download the data each week, and then it's jettisoned out of the capsule, and then the liaison gets the data and uploads it to us. Well, it turns out, Dell said the SD cards need to be a certain number of micrometers thick, and they were off by a couple micrometers by all manufacturers. They cost $30,000 to $50,000. We had 1 week, and we shaved all thousands of these little SD card plastic down in a timed press thing, adjusting this. You have to be willing to go the distance here. You need a small army to make sure you can get this technology working. The good news is it works, and does it ever work? So we loaded the chamber with these labeled SD cards, which crew member on which day in that, so we know exactly which one's jettisoned out, and there's a few minutes to do the task. So inside the chamber, they're wearing the ActiWatch for movement, which is used for sleep-wake activity, among other things. We're recording their performance and moods, and videoing the face off of the computer. And then this stuff goes onto the SD card. The SD card gets jettisoned out to the liaison. The liaison uploads it to a secure electronic site. They upload it to a quality control site where Pulsar extracts variables. We run quality control, deception tests, compliance tests, and then it runs to pen. We do the analyses, the plotting, and evaluation. All of this is pre-programmed, so within minutes of the data upload, we're looking at the final results. And we've aggregated it with everything else up to that point in time in the chamber. So we can see the profiles over time. We can see exactly what's happening. Now, what we're looking at, what I said, is performance, stress, fatigue, workload, moods, depression. We have to resolve what the base rate of depression might be in prolonged studies. There's predictions from Antarctica on what this should be with published papers. We don't know what it's going to be in chamber. Interpersonal conflicts, a long-standing issue. You know, it isn't that people have conflict. Of course they do. The question is how many go unresolved. That's the real issue. And then sleep quality. And then with the ActiWatch, and that data, by the way, we have 4,347 test bouts, 95.6% complete already. And then this is the ActiWatch data, sleep timing and duration, wake activity levels, and light levels on the individual. The ActiWatch is worn 24/7. They've been wearing it all the way. And we have 98.3%, 53,000 hours of ActiWatch data downloaded now, which we will share. Other investigators will run a model on it to detect circadian phase and other things, and these are European investigators, so there'll be more work done on it. I'm just going to show you a little bit of data without revealing anything. This is a profile of ratings of sleep quality. Good sleep quality, a visual analog scale would be down here. Bad sleep quality is up here, or poor. This is time in mission in day, and what you see is this is a good example of somebody that generally had good sleep quality. Now, keep in mind, these are self-reports. It's one of the reasons we also have the objective measures. We want to know, would the ActiWatch confirm this? We believe in healthy individuals who are otherwise honest, it'll be a pretty good match. We should see more movement and sleep, and this would be a much more variable. This is somebody that has a lot of bad nights. This is a weekly data we're showing you here, but they have a lot of periods when they're reporting bad sleep quality. So what's the basis of the bad sleep quality? Well, we don't know yet. Could it be free run, meaning their circadian system is running long, out of phase with the light-dark cycle and rest activity? They're not entrained to any Zeitgeber, and so they're going through periodic periods of insomnia. Could it be stress, worry, interpersonal conflict? What is it? And that's all part of what we're trying to answer. Here's a workload question. Both astronauts, these are the same scales we use in space, both astronauts and people we find love to rate workload. Workload is something everybody who goes into space or simulates or wants to talk about. This is a simulated mission with a lot of work. So you see that we can get variation in workload. Up is very high and down, and there are periods when it's higher and lower, and we can plot these at a much higher fidelity, but I'm just giving you examples. This is very high workload here. So we can get a sense of how hard somebody's working. We'd like to know how workload plays into some of the other behavioral measures in the chamber. Now this is interesting. This is ActiGraph data, ActiWatch off the wrist. And this is the daily hours of wake for one person in red. Here's the sleep, and here's their rest, a quiet resting, but awake. And what you see is an unbelievably stable pattern. That is a highly predictable individual. People, by the way, don't necessarily know this about themselves. And what they don't know is how different or similar they are to other people. Without objective measurement, they have no way of knowing. They guess, but they don't know, and self-reports don't help you here. Contrast it to that. Now, what else can you do with actigraphy data? Well, you can get sleep and wake. This is just to give you a little tiny sample of a whole bunch of stuff that'll be coming out of this study. We can look at activity counts per day, per hour, per day, and do a cumulative function. And what you see is one of the crew members is vastly more active than the others, is going up at a steady state at a much higher rate. Now, who would care about this? Well, if we're talking about long-duration space flight, and if we could show that the amount you move with a movement recording device on you is related to the bone loss, muscle loss, or something else, or ICP, or nearly anything, that would give us a cheap, simple way to get an idea of whether somebody's activity level is too high or too low relative to one of the other risk areas. It is a speculative area. It's sort of an area of potential serendipity to know, could the actigraph data turn into something useful for estimating other risks that might occur biologically in spaceflight. So there's a lot more coming from this study. In the end, we hope to have some very good information on activity levels, workload, stress, fatigue, sleep, psychomotor responses, stability, emotions, conflicts in an international crew. We also asked the crew to fill out a form before they went in, which they all agreed to, that's called a social desirability scale. Psychologists euphemistically call it a lie scale. And that's really a mean-spirited way to talk about it. It's a scale in which you are asked to answer questions about everyday events, but it's validated to tell us how you like to appear to people. How you like to present yourself, and people differ on it. And is it great? Probably not. Is it been heavily validated and used? It has. So it'll give us some information on whether those who like to appear one way are that way in the chamber or not. These are things we just need to know about behavior. Notice I haven't mentioned personality scales or selection or any of that. This is more behavioral ecology. What do people do? Not what do they say, what do they actually do? And then how does this relate to the crew's structure, hierarchy, and events in the mission? There's a lot of work to be done yet. We want to get to the end with as much data as possible. We are incredibly grateful to the NSBRI for funding this, and to the Institute for Experimental Psychiatry Research Foundation, which helped us get into this study at the time when NASA didn't have a legal mechanism by which they could support directly our participation. And then, of course, the IBMP for making this work so successfully, and we are very proud of the quality of this study. We think it will, in fact, be a very important study for understanding the prolonged effects of confinement. I would not venture a guess right now as to what we will learn, except to say that there may be surprises from some of our long-held ideas about the way people behave or what the quality of their lives are like in these environments. Thank you very much. I'm happy to answer any questions, but I'm sure Dr. Ushakov can also. Any questions about the overall study, the building of the chamber, the plans of IBMP, please direct to Dr. Ushakov. So it's been a long day. Yeah. Good.
How are you simulating off-nominal events, emergencies of sorts?
Спасибо, очень хороший вопрос.
Thank you. This is a great question.
Упустил его, честно
I
говоря,
have missed it, frankly speaking.
Ситуация нештатных
The contingency of nominal situations that we had over 350 days were a significantly great number. Some of them were serious contingencies, which were simulated mainly, of course. And there was also an off-nominal situation that was related to some minor failures, various technical devices, failures, or exercise machines. As you understand, this is very important. Computer technology failures or anomalies, sanitary and hygiene resources, and the rest that can be found on the simulator of the interplanetary complex. So the next off-nominal situation that was simulated intentionally, one of them was approximately 2 months after the beginning of the experiment or a month after the beginning of the experiment, there was a situation that was simulated related to the failure of electrical power failure systems. And the participants remained there without knowing how long it will last, for 24 hours, 23 hours, without any electrical power. And accordingly, one had to move equipment from refrigerators to other sites or other devices, and one had to somehow be able to prepare food and tolerate all the drawbacks that come with the loss of power. And the crew has demonstrated unity and good qualities. Also, the second off-nominal situation was related to one of those major complex factors where there was a complete loss of communication for an entire week. It was simulated. And today, Professor Gushin mentioned it in passing, and we also got very interesting data because we were able to find out that the crew was completely in autonomous flight, and it had tolerated that situation, which seemed rather risky or hazardous for us, that their tolerance of the situation was very successful. And so the impression that was formed is that they don't need the Earth very much anymore, and they can function on their own very well, and they can conduct experiments, perform analysis, perform all the operations related to training and work. And so the loss of communication hasn't led to any serious deviations. There will be some other off-nominal situations simulated, but I'm not going to mention them for the same reason as what Professor Dinges mentioned, that they are not going to be off-nominal anymore because they could get into the media, they could get into in print, and even though it's an indirect, there is an indirect risk, even though there is no direct risk, but there's a tangential risk that they might become known, so the experiment would not be pure any longer. Thank you.
Question? Thank you very much.